Hello class, this is Ms. Riggins with today's video on 1.6 fitting linear functions to data. Please remember to take notes and write your summary. Feel free to pause the video or to rewind or fast forward as needed. Your online whisk is due the day before the class that we start, so check the calendar to be updated. All right, let's begin. So today we're going to be talking about chapter 1.6, which is fitting linear functions to data. And here we have an example of 6 different data plots in which we call scatter plots. And what we want to do is we want to fit a line, which means to draw a line that can get through as many of the points as possible. So as you can see here, some of these lines are a lot easier to draw than others. And let me make this red so we can do this. Whereas for some of the data, it's going to be hard to get as many points as we want. Even though we can get a lot closer than other lines, it may be difficult. So in this case, we have an example of correlations in these 4 cases, correlations of linear functions, because we can fit a line to get through a lot of the points. These 2 are more stronger correlations, because we can fit a large majority of the points through the data points through this line. So we call these 2 ones strong correlations. This is strong positive, and then this is strong negative. But over here, we can't fit as many of the points through as we would like in the previous one. So we would call this, in this case, a moderate positive correlation and a moderate negative correlation. That has to do with the slope of the lines that we fit to determine positive or negative. Over here, it doesn't seem like we can fit many of the data points with a line, even though, and it can change how many points we can fit if we determine if we use positive slope and negative slope lines. So this is an example of no correlation, because we can fit about the same amount of points with a positive slope line than we can with the negative slope line. And down here we have a whole bunch of different points, and it would look like initially it has no linear correlation, but if we want to, we can actually draw, let me make this a color too. We can draw a curve, I guess I didn't make the color, to represent a nonlinear relationship between the points. So it wouldn't necessarily be a linear relationship, but it does represent a relationship between the points. So what we're going to talk about today is how do we determine what's the benefit of using these best fit lines. And the first thing we're going to take a look at is interpolation. If we have a fit line, then we can make predictions on the values in the data points that were not part of our data point. So another case, for 100, if the time is 120 minutes, what would be the height? Well, we have values for 0 minutes, we have values for 40 minutes, and vice versa, but we don't have values for 120 minutes. So if we fit a line through the data, then we could interpolate the value for 120 minutes as being 11 because of the fit line that we use. So when we make a prediction about the data within the data points regions, even though it's not the data point, it's called interpolation. But what if we want to make a prediction about the values that have no data points around them? Like, for example, if the minutes is 240 minutes. Well, then that would be called extrapolation. And extrapolation is very similar in the sense that we are still making a prediction, but this prediction is based off the fit line and points that are not in the fit line, or not in the data point range. So here we have 240 is not in the data point range. So when we determine that we predict that the height would be 6 centimeters, that's called extrapolation, because we predicted it using the fit line even though the data points was outside of the value we predicted was outside of the data point line. Okay, so what we're going to talk about today is this concept of trying to determine which fit line is a better fit, and how do we determine what that fit line is. Well, the way that you can determine if a fit line is the better fit line is by looking at how far the data points are from its actual fit point correspondence. So in other words, I know that seems like to be a lot. If we take a look here, right here, this is my data point, and this is where my data point should be on the line if the line went through it. So as we can see, there's a big difference with this fit line. But if I use this fit line and I pick this same data point, the distance between this data point and its distance from the line is a lot smaller than in this case. And the distance that we're using can be done either by the perpendicular distance like these are, or the vertical distance. So the idea is we are trying to determine which fit line gives you the smaller sum of the differences, and the differences are called residuals. The smaller the sum of the differences or the residuals, the better the fit. But how do we quantify that? Well, if I were to add up all these lengths of all these residuals, I would have a number. But sometimes people don't add up the positive lengths, they just add up the distance, and this is a positive distance, this is a negative distance. So sometimes people will, instead of just using the sum of the differences, they will use the sum of the squares of the distances, which is the differences, which we could do too. But we're not going to spend time with that, even though we could. We're going to take a look at the process of determining that information. Now, another way to determine how good the fit is by the correlation coefficient. And that correlation coefficient, let me move it down, is a number that we use as R that's between -1 and 1, and it measures how well a best fit regression line fits the data. And remember, regression is the process of determining a fit line. Well, actually, regression is the process of determining the best fit graph to the data, and a linear regression is the process of finding the best line to fit the data. Okay? So even if we find the best fit line, sometimes if the correlation is not strong or if the correlation is moderate, then that best fit line still isn't as accurate as we would like. And a way to determine how accurate the data is to a fit line, we can use a correlation coefficient, which is a number between -1 and 1, and it measures how well a best fit regression line fits the data. The closer to 1 means, or if it equals 1, that means the fit line is an exact fit of a positive slope line. And if the correlation coefficient is -1, it means that the fit line is an exact fit of a negative slope line. If the correlation coefficient is 0, then the data is too scattered to be any type of linear function relationship. Okay, and I have an example graph to represent that. So here is 1, that's exactly 1. Here is 0, here is -1. Now here is a moderate correlation, and as we can see, the correlation coefficient is not exactly 1, but since it's increasing, we say it's around 0.6. And since this is a negative slope line, in this case, the correlation coefficient is around -0.6. But just because the correlation coefficient is 0 doesn't necessarily mean that you have no relationship. It just could be no linear relationship. This 0 means no linear relationship, but these zeros also mean no linear relationship. But we can see this looks to be a quadratic. A little bit later, you can see this is a circle, and this is a hyperbola. We'll get to it later. So I wanted to show you how we could use the inspire to determine the best fit line as well as the correlation coefficient. I'm not going to show you how to do these calculations by hand when we have the inspire to do that for us. So here we have some data, the data between the relationships between the number of hours a student studies and the score they received on an exam. And we have actually 15 data points. So to see the graph of the data points, we would need to add a data and statistics page. So we hit Control-I and add a data and statistics page. And as you can see here, we have our 15 data points all scattered around. I'm going to go ahead and let the x-axis be the hours and the y-axis be the score to see if hours is the independent variable and score depends on hours. And then as you can see here, now we have our scatter plot. To find the best fit line, the calculator uses the least squares. And that will basically find the better fit line if one exists. So in order to determine that, I hit Menu, Analyze, and Regression. And then I want linear, so I can either use this form or this form. It's the exact same one. So I want to see the linear regression. And not only do they show me the linear regression, but they graph the line and they show you what it is. Now, some of you may say, it doesn't go through as many of the points, and you're right, but if I were to take a sum of the squares of the residuals, this would give me the least number. And just trust that this is the case for this situation. And as you can see, the relationship here is not a strong positive correlation. It's a moderate correlation, positive correlation. But this is the equation in slope-intercept form. Here's the slope and here's the y-intercept. So if I wanted to see about the correlation coefficient, I would have to add another page. So I'm going to Control I to add a calculations page. And I'm going to hit Menu. I'm going to hit Statistics because correlation coefficient is a statistics. I'm going to do stat test and I'm going to hit linear regression t-test. Now, they're going to come up with the window to say, well, what data are you talking about? And I'm going to put X for hours and Y for score. And I can save it to one of the functions if I want to graph it later. And I can do the F1, F2, or F3, doesn't matter, or F1, so I can do F4 just to be different here. And then I'm going to hit OK, and don't worry about the other stuff. When I hit OK, as you can see, it comes up with some information. The linear regression test, this is the equation in linear format. It gives you our A, which is our y-intercept, and B, which is our slope, even though they kind of switch it around that we're used to. But then if I take a look at R, I get R, which is a 0.69. Which means our data is not a strong best linear data correlation, but it's moderate enough. Okay, so that's the video. I'm sorry it's a little bit too long, but we had a lot of information to cover. All right, thank you.